when we have when we have very limited label data. And it has been demonstrated in different applications that if we train the machine learning model in that way and then adapt to specific tasks, it can enhance the accuracy of the downstream model significantly. As we can see, most of the application that use foundational model at the moment, like ChatGPT or other type of diffusion model that generate image, those model first train with the raw data with self-supervised learning, and then they adapt that to different tasks like question answering or video or image generation. But so far in this machine learning community, usually people focus more on text and image. While in scientific discovery or in enterprise application, there are more than just image and text. So that's the topic of the talk today. I will talk about different kinds of foundational model that build on the top of more complicated data for scientific discovery and also for enterprise application. So the talk will be two parts. In the first part, we will talk about our recent work called auto knowledge. This work is about to try to learn good representation of knowledge graph or multimodal knowledge graph from scientific data with application in drug discovery. This is our joint work with our lab mate, including Marcos, Mai, and Raul. Raul basically was from the UCD, Rodrigo and Vanessa, and also two colleagues from the Zurich Research Lab, including Cesar and also Michele. Yeah, let me move this a bit. Yeah. This is the main motivation behind our work. As we know, scientific data is very complicated. It's highly multimodal, right? Come from different sources. You can see in this slide an example of different pieces of scientific data. It could be a piece of data come from simulation. It could be open knowledge base. There are many curated open knowledge base available. For example, Campbell is the database of drug and information about different kind of drug with the property and so on. And also UniProt is the database of protein, where we can know more information about protein, its structure, its property, interaction with each other, or interaction with drug, for example. And in science, usually we publish paper, right? So we see scientific article is a very useful source of knowledge. As you can see here, this is a piece of abstract from an article. It includes a lot of useful information. The main question is how to basically leverage this type of data for training the AI. And also, not only the data is from different sources, but also the data have different modality. Even for a small piece of molecule, as you can see here, it can be represented in different format, right? It could be a string representation like a smiley representation, or a 3D representation, or 2D graph. And it can be associated with a text, a speed of text that describes its function, its property, and so on. Those rich information can be used to train AIs, of course. But how to do that? This is the main objective of our work, and how to basically learn a good representation from those rich data and then transfer that to different downstream tasks, especially for drug discovery, for example. This is why we build a system called auto knowledge. This is an end-to-end system where we allow to ingest data from different sources easily, leverage different kinds of pre-trained foundational model, and then enhance those pre-trained foundational model with information from the graph that we build to transfer that into the downstream task. So we start with different database, right? Imagine like we have a lot of database like RackBank, UniProt, I explained before. That could be Campbell, BindingDB, in ontology. They link somehow, right? But how to ingest them and bring them together and build a single big multimodal knowledge graph so that we can learn a good representation from that knowledge graph. We build a system to do that. And then every piece of data in the graph have some information about, for example, for protein, we have sequence information, we have textual description of protein, we have 3D structure and so on. Every of that we call a modality. And every modality, usually there are a lot of pre-trained model to learn the representation. I mean, the vector representation of that modality that can be used further for training. And that's where we have a model zoo. In the model zoo, we keep different type of pre-trained machine, pre-trained foundational model. This is the model that trained with a specific type data like sequence data, structure data, right? Those providing initial embedding of the entity of interest. But that initial embedding does not contain any information about the, the, the database that we have here. That's why after creating the graph neural network, we further enhance the initial embedding representation with the graph neural network. And the graph neural network is trained to predict the topology of the graph, also different information in the graph. That's why it tries to learn a concise presentation of the entity in the graph so that it can be transferred to different downstream tasks, as you can see later in the slide. Yeah, this is an example of how we create multimodal knowledge graph from different sources. What the user need to provide is a schema, where in the schema they need to define the entity and the relation and the modality associated with the data properties. For example, if we have in this toy example, you see two different data sources, right? One is the UniProt and another is the RUG. This is tabular data, but the data can be in different databases as well. In this case, the user defined two different entities. One is the protein come from the first table, and second one is the drug come from the second table with associated data property. For example, protein have some taxonomy information. It may have interact with relation with the other entity drug in the other table, and then it may have some sequence information. For RUG, we have some textual description, we have some smileys information, we have some 3D representation. So with the simple schema definition like this, we can define the graph. But most importantly, for every data property here, for example, for a protein, with the sequence information, we can define the modality. The modality here, if you remember, we have a model zoo, and inside that model zoo, we have a set of different retrained model that can automatically transfer the sequence into the vector embedding for the machine learning algorithm. Right? So this is the data ingestion part. This is important because every time we deal with new data, we need to have a simple way to integrate data from different sources and define different modality. Right? In the model zoo, at the moment, we have a lot of pre-trained model for every type of data. And mostly they are the pre-trained model for biomedical entities. For example, for drugs and small molecules, the machine learning community created new pre-trained model every week, so we can include them. For example, we have Morphomer is the popular type model that deal with the smileys and can transform the smiley into vector representation. ImageMo is the one that look at the image of the small molecules and transform that into vector presentation. Unimodal, on the other hand, looking at the 3D presentation of smileys. And the graph MVP, another one that working on the graph, the 2D graph structure of the rock. And those are different example of pre-trained model for unimodal, right? Because they just work on a database of a specific type of modality, right? For protein, we also have a lot of model that we supported. Most of them is for sequence, but some of them also work with the 3D structure, event 3D structure data for pre-training. The protein foundational model is quite scarce. Also, there are models for DNA and RNA as well. We're also working with material science and also looking into adding them into this set of supported model in the model zoo. Okay, so once we have created the graph and then use the pre-trained model to transform the data into initial vector representation, what the graph neural network does. In this slide, you can see a toy example. In this toy example, there are three entities. You can imagine like there's a protein. This is a blue knot. The second protein, they interact, right? This is the information that we can get from some database like UniProt. And then there's another rock that the yellow one interact with this protein because this is the target. This protein is the target, this rock. Every node in the graph may associate it with some data property as well, like this rock have some toxicity information, it in numerical value, and then it may have some smileys information as well, right? This is a smiley string. The protein can have sequence information together with some textual description of the protein, right? So this is a multimodal noise graph because it have different information from different modality like text, like sequence, like smileys, and more, right? Our framework is very generic. Now, what is the role of the model in the model zoo? The model zoo, for example, it takes the sequence information and then it transforms. This is one of the modalities or the model in the model zoo called ESM, released by Facebook, by training on huge database of protein sequence. And then that transforms the sequence information into a vector representation. The same thing for smileys. Smileys can be transformed to vector representation using different pre-trained model. In this case, for example, that given by a Morgan fingerprint is typical fingerprint that turn a string of smiley into a fixed size vector representation. Now, all of them need to be transformed into the same space, right? Because they have different dimensionality and so on. So we align them using multi-layer perceptron to align them into the same space. All of them basically follow the same MLP to basically transform into the same space. That's the initial embedding. That initial embedding, for example, like the ESM was trained on a database of sequence. When it trained on a database of sequence, it learned the inherent structure inside the protein, but it doesn't know additional information that provided by the graph that we built, right? For example, it doesn't know that this protein interact with this protein, for example, and this drug is this protein is target of the drug with this kind of toxicity. That additional information can only be used to enhance. If we look into this graph and then enhance that with the graph neural network, if you're familiar with the graph neural network, the way it works is like this. So the graph neural network will work by asking the network to propagate information in the network and then predicting different information in the network. For example, it can predict a link. It can predict data property, right? And in that way, the graph neural network can leverage the contextual information about the protein. For example, starting from initial representation from sequence, the graph neural network is asked to predict this link, right? The same thing happened here for drug, starting from the Morgan fingerprint or the ESM representation for this protein, it asked to predict this link or predict this the toxicity information. In that way, it incorporates additional domain knowledge information into the initial representation that given by the other modality, right? Which is which is uh, which is basically need to be very compact and efficient to incorporate the knowledge about the graph inside a new representation once it is trained. So we train this graph neural network using multitask learning. At the moment, it supports basic tasks like predicting the numerical value in terms of, for example, in this case, toxicity, just a number. It predicts the link, right? A link prediction problem. And then it predicts the categorical value as well. We're planning to extend this to predict not only those basic information, but more complicated information like it predict a piece of text, for example. Even if we have this presentation, we can predict and we can fingerprint and other information in the graph. If we make the representation more compact and then it's rich. Okay, that's it retraining with the knowledge graph that we build. But what is the application of that representation? In general, we know that there are upstream model, I mean the model that train with the self-supervised learning and learn compact representation of the entity in the graph. And now we have the downstream model where there are different downstream tasks with label, right? As for example, one of them is given a pair of protein and rock, how to predict the binding affinity, mean how they bind together. Let's see, binding affinity is the way to measure the drug effectiveness. When it binds to a protein, it kills the virus or bacteria, right? There are a bunch of predictive modeling that's based on label data. And the label data in this case usually is very scarce. It could be a few million of pair, right? In general, we can leverage the pre-trained model. In this case, because we already pre-trained the transformation of sequence, right, into a compact representation, we can directly copy that part of the graph. Basically, this is the case we transfer directly the subcomponent of the graph neural network into the downstream model. And there are different ways to do so. But so far we see that transfer the subcomponent of the graph neural network is the most effective way to transfer the knowledge. Now, other popular type of transfer is basically just taking the representation, but we lose a lot of information by transfer the representation from the upstream to the downstream model. We did an evaluation of our work. This is one particular application called binding affinity prediction. As I explained before, given pair of protein and rock, we need to predict the affinity. That's a regression task, right? In this field, people created different kind of leaderboard. One of the popular leaderboard is called TDC binding pattern leaderboard. This is published in NeurIPS 3 years ago. And it had a challenging split because the data was split by temporal information. The way they do is they get the data from the patent and then split the data by the patent date, right? The training data, including the data that's basically before the patent cutoff, or patent date cutoff, and the test is the rest. We train auto knowledge with 5 different public knowledge graph. And the team created different knowledge graph. As you can see here, there is a small statistics for every graph. The first one is called UniProt, BindingDB, and Campbell, right? We also consider PrimKG is the one that recently created from Harvard University. Dude is very small one, and Stitch is another one that kinds of virtual graph that extracted from scientific literature and also BindingDB as well. What we do is we do preprocessing and remove the potential leakers because there could be overlapping between the test data of the TDC patent and also the data inside the graph that we created, right? So we we remove the overlapping to avoid leakage that may happen. And we release the knowledge graph in our website as well, together with the pre-trained model. The result that you see over there in the leaderboard is rank number 1 at the moment, is the example of 5 different knowledge graph that basically we see that this is more robust when we make an example of them, because different graph provide different type of information that might be complementary to each other, and it's yield the best result at the moment. Right? This result will published in the AAAI conference. We release also the data and also the model that we train on 5 different knowledge graph. So this is the initial part, right? Where we have showcase of building multimodal knowledge graph and showing that it worked very well in a particular use case here. As a future work, we plan to extend this to new domain, not just in biomedical application, but also in material science and other scientific discovery domain as well. This concludes the first part of my presentation. Before moving to the second part, I would like to take some question if you have from behind. Maybe. You see?
Yes, so I just want to explain that we are recording this talk. So if you ask question here, then you allow us to record your question and release it on YouTube later on.
Yeah, I see.
Okay, Vinh.
Vinh, right? Yeah, please go ahead.
Summarize correctly if I'm wrong. If I understand correctly, the main difference here is instead of on-type self-supervised learning and transformer-based techniques that people own use in foundation model, right? Here, the main difference is we put another layer from the GNN, right, to try to learn from graph data. And if I understand, is the key differences or any something that I missed? Thank you.
Yeah, thank you for your question. Yeah, exactly what you stated before, right? We in general, we have some pre-trained model. Most of them is basically transformer. Some of them is not, like graph-based or 3D-based information. For example, this one is the transformer-based model, but for small molecule, it could be 3D model, graph model. And the idea is there are a lot of them, and the graph have additional information than just some unimodal, right? So we enhance them with additional information from the graph, but also fuse information from different modality as well. That will make it more powerful than just use a single model in the setting that we just take the transformer, right? Yeah.
Yes. So Alex, you want to ask your question now?
Yeah. Thank you very much.
Yeah. In the interest of time, I think we just take the question from Alex, and then we continue with the talk, and then you can ask your question at the end, right?
Yeah. Yeah. Please go ahead.
Thank you very much. Alex Cronin from UCD Center for Cybercrime. I was curious if some of the resources that you have in relation to training the models and the orchestration of the models in a containerized environment or things like that are publicly available on the links that you distributed in the talk, just so that I could look at augmenting them and using them in a cybercrime environment.
In the cyber environment, you have what kinds of data usually?
So we've large amounts of multimodal data, each of which could indicate what you call a possible action in cybercrime or a threat. And then a lot of that data would be unstructured. And then we'd be looking to process that data, relate different unstructured data sets to one another, or heterogeneous data sets to one another. So it's about it's curious as to whether or not you have some tools or some containerized applications, or some frameworks for customizing models, so that we could swap out the data sources that you're using here for our own data, and leverage your very good work in terms of the communication infrastructure between the heterogeneous networks.
Yeah, I see. We don't have the containerized application yet, right? It's for the application that you are interested in. I think it's quite interesting, and I would like to learn more about that. I think we can take it offline. I can contact you, and then we can talk more, right? And see whether there are ways to basically include new type of data, especially different modality that you are working with. And what kind of pretrained model? I'm not sure whether in the cyber security there are any kinds of pretrained model available for the type data that you are working with, right? Especially the model zoo, right? If you look here, at the moment, most of the thing in the model zoo that we support is basically for some for text, some for sequence, protein sequence, and also small molecule, right? Maybe we can take it offline, right?
Thank you very much. Yeah, I'd really appreciate that.
Yeah, thank you. Okay, yeah, may I continue with my presentation, right? In the second part. Okay, this is the work that recently we have done with students from Vietnam National University, including Quân and Sương, right? They are they were undergraduate students while they're doing this work. Now they already graduated. Now, also the work's done with Lâm Nguyễn and Dũng Phan from Yorktown Heights IBM Research Lab in the US. We have a GitHub with more information and with a preprint if you are interested, and also the open source framework. Okay. So this is highlight the motivation of this work. In general, all we know that tabular data is very popular, right? Many of the time we put our data in tabular format. Even in industry, it's very popular as well, like insurance, like banking system, their transaction data, or in relational database with a lot of table data. And most importantly, the tabular data include kinds of knowledge that often cannot be represented by other types of data, because it's the private data, and it has information that not just a single piece of information that can be represented. For example, correlation between disease and different behavior events, for example, in the electronic health record. And the foundational model trained on the image, on the text, I'm not sure that it can learn this kinds of knowledge. But basically, we need to look at additional data to train the model to learn this type of knowledge. And so far, this field is very underrepresented, because mostly due to the fact that the data is very noisy. It's very challenging to deal with this type of data. For example, we have a column with the income information. Imagine like you have income information from different industry. They have different distribution. They may have different currency, right? So the scale already different. And even the data can have a mixture of different things, like can temporal information, textual data, along with numerical and categorical data. And even the category in a table, it can be encoded in different way. Let's give an example, like education status, right? Usually in different language, it's already different. And also, even just a master of science degree, it can be encoded as master degree, Master of Science, MSc, and so on, right? Because different way to present the data, scale, the noisy information, people don't believe that there could be something that transfer across the database, right? Across the table. And learning algorithm is very sensitive to those changes, right? In a position table, in a position paper in ICML this year, Boris van Prugel and his colleagues have a position paper that's quite interesting, asking the question why tabular foundational model should be the research priority, right? He collected some statistics about the paper accepted at top machine learning conference, and different modality you can see here is that concerning foundational model, right? You can see the growing number of foundational model for text very quickly, for image, even for graph, right? There are some work from time series and inside IBM. There are some group working on that as well. But tabular data is underrepresented here. This is an important problem, challenging. So that motivates us to work on this. We started this 3 years ago, right? But the student need time to get familiar with the stuff, and then we get it done now. So the problem with this field is that not only less attention, but also there are lack of clean data set to train foundational model, clean benchmark data set to benchmark them, right? And a framework to build what algorithm and things like that. So that is the main goal when we build a tabular FM, is the system that allow people to benchmark. We curated different types of table. We took data from different sources like Kaggle, from Kaggle competition, and then GitHub table, curated them, and create a clean data set for building tabular foundational model. And then also create the benchmarking data set, because we want to know which algorithm, which learning method would be better than the other. We need them, because different work usually use different benchmark, and it's not easy for them to compare across each other. Also, we create a leaderboard for comparison easily, right, with some standard method and the reported result. The framework is open source. Also, some pre-trained model is in the hacking phase. You can take a look into the tabular FM website to know more if you are interested. I'm going to talk a bit about data curation. This is the part that we spend a lot of time, because tabular data is very noisy. First, we grow 40K table from Kaggle. Kaggle release the data. Usually they allow people upload the data, and then it's in tabular format, but sometimes it's not very clean. It can contain a set of tables rather than just a single table, right? So data cleaning is needed. We also leverage another corpus called Git table. This is the table already downloaded from GitHub. It's also noisy, very noisy as well. So we remove noisy columns such as textual information, timestamp, a lot of IDs column that doesn't make sense to keep, and a lot of column that with categorical information, but that is too sparse to keep, so we need to remove them. As the problem, as we discussed before, that numerical data might be very come from different scale, right? The income in different currency, different location, different industry, and so on. So we need to standardize them. And one of the way to do that is to fit a mixture of Gaussian on every numerical column, and then assign the value to the Gaussian distribution that belong to, subtracting by the mean value and divide by the standard deviation, right? In this way, most of the value might be having different scale, but after that calculation, they look similar because distribution, if two columns have similar distribution, after this kind of curation, value very similar. Another problem that we got is because data is grown from Kaggle and also from Git table, usually they may be overlap, right? We cannot control that because people upload their table without considering whether there are some redundancy or not. It's very difficult to check. There are many variations of the same table. They delete some column, they do some transformation. It's not detectable. And the way to avoid to do that at the moment is to avoid a leakage that may be happen across the training and the test set split, right? Is to looking at the label of the table. There are some meta information not on the Git table data set, but on the Kaggle. That's quite useful. And we took the table name and also meta information, take the word embedding, and then cluster them. After clustering, you can see this is an example of projected cluster on a data set. It clusters nicely into cluster, right? For example, this one is the data set that related to medical diagnosis and prognosis data sets. In that way, we split the data not randomly, but basically by the cluster. You can see here we create different versions of the data set. This one is for split by the cluster. And since the data is very noisy, you can see some statistics to know how noisy they are. For example, this is 40K table down to only 1,400 after those data curation method. Right? The Git table also the same thing, because usually in the Git table, if you look most of the case, even the data is stored in tabular format, it could be just a single column with the Amazon product review, right? Textual information rather than something that related to tabular data. We have to remove them. And we release the data under open term, except for the cargo data set. If you want to benchmark or do a research with it, you can send an email and then we send the piece of data to you, right? Because it's restricted to the cargo license term. Okay, in terms of learning algorithms, we look into different literatures and we see there are 3 types of learning algorithms popular for this type of data. The first one is based on the GAN generative model. Second one is based on variational autoencoder, right? This is 2 popular types of generative model. And the last one is based on transformer, because there are always the question whether the transformer is really relevant for tabular data, right? At the beginning, we don't think they are, but let's see. An example of how transformer is used here is quite interesting, and this is in this work by Vadim Borisov. He transformed the tabular data into kinds of text data, right? It's not even really text to use the transformer. For example, this is a thought example where we have a table with income, education, professional, and location, and things like that. Right? He transformed into the text by simply taking the header of the column, put into the value, right, and concatenate them in this way. You can see income is 120K, education, master of science, and so on, right? And then he do random masking, like the regular masking when we train the language model, just mask the value rather than masking the header, and then asking the transformer to predict the mask value. Yeah, the question is whether there are something like this is useful for learning transferable across different tables, because since that if there is no data preprocessing, probably it's very difficult, right? Because you see here, profession, this is software engineer, right? Yeah, maybe it's encoded in different way, but just mean the same thing. We probe the performance of that 3 types of algorithms. The first question is whether retrain on the tabular data really help, right? This is the main question we asked at the beginning, because for text and image, this is clear, right? But for tabular data, we don't know. There are many 2 factors, and this turns out to be that there are some positive results that we got so far. So if you look at this plot, you can see here, this is the overall score. This is the generative model. It's measured by how matching the generative data and the original data, right? Just the higher score, the better, something like that. We have the purple one is the performance of pre-trained model. That means pre-training with the training tables, and then test on the validation and also on the test table, right? Remember before we have the split that among 1,400 tables, and about 900 tables used for training, and 140 tables used for validation and testing. we had this is the result of the GAN model, right? To compare the result with retrain and training from scratch, we can see that there's a clear benefit of pretrained model, right? You can see here, and also the larger the model is, there are two versions of them, small and large. The larger the model is, the better result, right? This is consistent with what people observe in the language model. When they train with larger model, retrain also better, and larger is better. This is the variational autoencoder for specific test table. Every of the subplot is a test table. For example, this is the survey information. In the plot, I'm not sure if you see it's on the presentation. It's very clear. We consider the pre-trained and from scratch, right? You can see here the pre-trained model. This is a learning curve in terms of the training loss over the box. You can see that the pre-trained model that can catch better with the learning, and then the loss degree much faster, right? This is early termination, so it stopped before even not going further, but it's still better, right, for this data set. For some data set, I think, for example, for this one, maybe too small, not necessarily pre-training is better in this case, right? This one is still going down a bit, and it's not always better. It depending on the characteristic of the table. But if we look further into what it can transfer and when it transfers better, right? This is looking at a specific data set with the column. You can see here, this is customer data with the gene and age, right? And then it compare different information. The blue one is the real distribution of data, and also the predicted value using pre-trained and training from scratch, right? You can see this is the case for the variational autoencoder. With training from scratch, it's mostly predicting the mode of the distribution. The distribution of data for us look like a Gaussian distribution in this case. And if we do training from scratch, it predicts most of the time is the mode, right? But with pre-train, it can fit better to the real value more than the training from scratch. The same thing here, you see, for example, for diabetes here, there's always if the data is too small, the variational autoencoder seem to just try to predict the mode of their distribution. That's what we observe. If it is not pre-trained. In terms of learning algorithm comparison, so we see so far the question of whether there is some transferability or not. We already answered yes, there is some transferability ability over there, and it's very clear. Now, which algorithm would be the best algorithm? At the beginning, we don't think that the transformer can do a good job because we didn't do any data preprocessing for transformer. But surprisingly, it worked really well. You can see here with Git table and with the cargo domain split, right? At the moment, the ranking of CTGAN, it also compared with different model size as well. CTGAN is bigger than variational autoencoder. So so you can see here the performance of CTGAN and Cray is the top at the moment. We also have different version of variational encoder that basically we call share TVAE. In general, that is included also additional meta information about the column in addition to only the table itself, because you know that the transformer it learned by looking at the header, right? It know what does mean by that column, right? They're looking at that. So we also try to improve TVAE by adding the embedding of the header into the variational autoencoder, but it seems that it doesn't work really well in that case. So because the transformer is have a lot of contextual information. This is based on the GPT-2 that retrained on the last textual corpus, and it's interesting that it transfers some knowledge from the text to tabular data, and it do very well in both of the case, right? And this is interesting. That means if someone want to develop tabular data foundational model in the future, should focus on the transformer, right? And we are trying to expand this. At the moment, we're training with bigger data set with 200 million tables, and let's see what happens in the near future. And this is the last piece of the talk. In general, we know that there's some transferability. There are algorithm that one is better than the other, but one of the questions that we want to clarify is what kinds of knowledge, that can be transferred and cannot be transferred, because we know that in the case of text, we know that what the language model learn is the general knowledge about the physical world, and also it learned the syntax from the text, because there are some work saying that when we try to approximate the attention layer of the transformer trained on text, it basically approximate the syntax dependency tree, right? So that is how we know language model work. But in the terms of tabular data, what kinds of general knowledge that can be transferred and what kinds is not, right? So we look closely at the result and try to plot the dependency between the information between the column in the table, where because in the metric that we evaluate the model, there's a metric called the correlation trend. Actually, it measures the correlation between pair of column of the synthetic data and the real data. And if that trend is matched, then we know that it transfer that type of information, right? If that trend is not matched, it not transfer that type of information. And if you look at this plot, there are interesting information it can transfer. You see the purple one. Every block of purple here is related to the healthcare. For example, here is the community health center, public bed, district hospital, urban population, urban hospital population, rural hospital bed. Yeah, everything is connected, right? And let's look at the blue one. This is polydipsia, polyuria, sudden weight loss, facial paralysis, right? This is basically all related, nicely related. And those are the general knowledge that can be transferred. It's interesting. I'm not sure with text we have this kind of information, maybe. But for tabular data, it could be very interesting to see what kinds of knowledge that can be transferred from tabular data, but not can be found in the text web. Now let's look at the thing that cannot be transferred. Okay, this is non-information. This is, let's look at it. For example, let's see. Okay, this is TV and radio. I'm not sure why they are related, but it's not transferred. Difficult for the model to learn something related from TV to radio, right? This is tempo loudness. Maybe because they're in the training data, there are no such thing, so it's difficult to transfer. This is rural hospital bed and latitude. District hospital, government library, right? Private library, right? I think in general, this is some, we don't have a clear explanation for this, but the intuition is this is too specific knowledge that more difficult to transfer. And this is more general knowledge that quite popular, and then it's easy to transfer than the other, right? So now we know that in the tabular data, there are kinds of information that can transfer, kinds of information that not popular cannot transfer yet. And this is the reference of the work that we have done. One is published in AAAI this year. Another one will be present as an oral presentation at ACS4. And also we have the preprint on archive for the last work on tabular foundational model together with the pretrained model, and also the framework to build and benchmark the tabular foundational model. Right? Yeah, thank you. And I would like to take a few questions more on this topic if you have some.